This is 2018 IMO problem number 1, and here is a view of this problem. We're given the circumcircle of triangle ABC, and we mark the points D and E on the sides AB and AC in such a way that AD is equal in length to AE. What I did was to color AD and AE in green so that I don't forget those two segments are just congruent. Okay, then we draw the perpendicular bisector of BD. We let it intersect the circle at the point F. And similarly, we draw the perpendicular bisector of EC when we let it intersect the circumcircle at the point G. And again, so that I don't forget that, that this is a perpendicular bisector, what I did was I connected FB and FD. So those two measure the same length. So that's why I did draw them in red color, right? So FB equals FD, and similarly, because G is on the perpendicular bisector of EC, EG is equal to CG. EG is equal to CG. And lastly, we want to show that DE, E, and FG are just parallel to each other. I'll provide two different proofs. The main idea of the proof is if you want to show that say two lines are parallel to each other, let's say line L and L prime, one method would be to just draw a transversal and check the corresponding angles, right? If I can show that the corresponding angles are congruent, then that would show that N, L, L prime, those two lines are parallel. So therefore, to show DE and FG are congruent, you can check corresponding angles. For that, what I will do is I'll go ahead and extend. So in my first solution, I will extend FD. Well, actually, I don't want to mess up my the fact that FD is equal to FB. So let's just go ahead and extend it with a different color. So we have FD extended. I'll let it meet all the way to that circle. And similarly, I will extend EG as well. And I would let it intersect the circle as well again. So let's call these points as, say, X and Y. We haven't used those letters yet. Okay, so these are the points X and Y, and we can call this intersection point as Z. Awesome. And now we can start chasing the angles. I would say let's start with say yeah. Okay, before I chase the angles, let me also connect AX and AY as well. Okay, so now we are in good shape. Okay, so let's start with this angle here. So angle AXF subtends minor arc AF. As such, it's equal to angle ABF, right? So let's write that down. AXF is equal to angle ABF. ABF. But then, because triangle BFD was isosceles, ABF is just equal to FDB, angle FDB. And again, by vertical angles, angle FDB is supposed to be equal to angle ADX. Angle ADX. So therefore, we have shown that triangle DAX is isosceles. Triangle DAX is isosceles, and as such, AD is equal to AX. But wait, AD was equal to AE, so therefore I probably should also color the segment AX in green, so that again I don't forget that AX is equal to AD. And by the way, like I said at the beginning, AD was also equal to AE. Well, I can do a similar analysis on the other side, right? Okay, so let's quickly do that probably. So if you check angle AYG, this angle is obviously congruent to, because it subtends minor arc AG, that arc is also subtended by this one, GCE, or GCA I should say, but GCA is equal to GCE, which is equal to GEC, but then by vertical angles, GEC is just AEY, and boom. So again, similarly, okay, so similarly, we get that triangle YAE is also isosceles. YAE isosceles as well. As such, again, AE is equal to AY as well. Okay, let's do that. AE is equal to AY, another green congruent segment, right? So from the first one, we got that AX is equal to AD. Oops. AX is equal to AD. And now we get that AE is equal to AY. But wait, AY, like I said, AD was equal to AE. So all these four segments are actually congruent to each other. 1, 2, 3, 4. So all these four segments, they are all congruent to each other. That suggests, therefore, we have a circle centered at point A, right? Which goes through the points Y, D, E, X. So therefore, Y, D, E, X concyclic. Okay, so Y, D, E, X concyclic, and the center of that circle is the point A. I can just do a really quick rough sketch of that circle. I don't really care how it looks like. All I care is the fact that I can now chase angles based on this circle. Okay, there you go. Let's try again. Something like that. Okay, there you are. Okay, this is a horrible circle, but it will do the trick. Now in the second part, now we can further chase the angles. So what I want, my strategy, my plan is to show that this angle YED is equal to angle YGF. Okay, so well, we can just start with angle YED, and clearly that's YED is equal to YXD. But okay, so let's write that down. Now angle YED is equal to angle wait, where was I? Oh yeah, YED is equal to YXD, right? So why is that? Because they subtend the same arc on that new circle, right? So YXD. But YXD is equal to YXF if I move to the other circle, and YXF is just YGF, right? So obviously they subtend the same minor arc YF. Remember, that was the point Y. So YGF, angle YGF, and boom, that's it. So we have just shown that YED is equal to YGF, and obviously, so that would immediately establish. So therefore, this establishes that DE is indeed parallel to FG. Awesome. So that's one way. So we have just shown that this angle is congruent to this angle, and that established that parallel idea. An alternative way to establish the result is again, so this is due to an AOPS user. I forget it's his name. Something. Sorry for that. I totally forgot his name. But so there are dozens of solutions on AOPS website, and obviously this is not a hard problem at all. So well, compared to number 6, which I'm planning to solve probably in the next day or two. So this is IMO number 1, solution 2. For this one is like an interpretation problem, but it will do the trick. So let's go back and re-establish the congruent segments. So we early on we know that F is on the perpendicular bisector of BD. So like we did earlier, let me just color them. So FB is equal to FD, and by the same token, I forgot which color I used for the other one. Oh yeah, it was a weird color like this. So, and similarly, oops, GC is equal to, oh gosh, okay, GC is equal to GE. So let's consider the following now. I think I'm just focusing on 2 triangles. Yeah. So before I focus on those triangles, I better extend these perpendicular bisectors. So I'll go ahead and extend this one here, and let's call it what, y, I think I called it y, this one, and when I extend this one, pretend I call this one as x. Why did I say pretend? I don't know. Okay, and now let's consider the following two triangles. The two triangles I have in mind, the first one is triangle GAY. So let's go ahead and, actually, let's just focus on that triangle for a minute. Yeah, so GAY. So GAY, so triangle GAY. On that triangle, well, first of all, the circumcircle is still that circle. The circumcircle is the same of the circumcircle of ABC, right? And now focus your attention on AC. AC is the altitude to that triangle AGY, right? So AC is the altitude. And can you guess where the orthocenter of that triangle is? So I need the orthocenter of that triangle. Well, by a well-known property, we know that the orthocenter must be such that if you call this point, say, K, KC is equal to KE, right? So this is given in the problem. This is exactly the property of the orthocenter. So that establishes that the orthocenter of triangle GAY is just E. That's pretty decent. And by the same token, by the way, if you focus your attention on triangle FAX, well, let's also draw that triangle, I guess. So that one, FAX, at the risk of making look the thing complicated, FAX. Do you guys also see that the orthocenter of that triangle is D? Simply because, again, D, if you call this point as L, sorry for that, DL is equal to LB, right? So let's write that, because DL is equal to LB, and this one because what? Because what did we say? EK is equal to KC, and C is on the circumcircle of triangle GAY, right? EK is equal to KC. Awesome. So after these facts, now we're in business. So consider the two triangles again. We have segment AD and AE are congruent. Okay, so this one requires a little bit of bashing. So if you have a triangle, let's quickly do the bashing. So consider a triangle ABC, just a generic triangle. And whenever you drop the perpendicular here, call this D, and you obviously have somewhere, let's see. So somewhere here is your point H, the orthocenter. Okay, let me just complete the whole thing. Hold on. Yes. Okay, now my claim is that, I need to show the length AH. Okay, so let's consider, so this is E, this is F. Let's calculate AH in terms of the side lengths of this triangle ABC and the angles, right? Well, one thing, so these are all 90 degrees, so let's first establish that before we forget. Obviously BFHD is cyclic, as such this angle is B, angle B. So as a result, I can start, for instance, with the sine of this angle. So sine of B is sine of angle B is just AF over AH. AF over AH. But as I said at the beginning, because my length of interest is AH, so let's just refocus on that, is just AF over sine of angle B. But then AF, if you focus your attention on right triangle AFC, because this whole angle is A, right? So that's just equal to AF can be replaced with AC, which is the hypotenuse cosine A. AC times cosine of angle A divided by, actually, you know what? I'll just divide it by sine B, but I'll just do it like this. And you know why, right? AC over sine B. AC is just side B, right? Side B, this side, divided by sine of angle B. That's just the extended law of sines. This is just 2R, cosine of angle A. Aha! So therefore, the distance from a given vertex to the orthocenter is just 2R, 2 times the circumradius, times the angle, this angle here. So for that reason, the length AD, let's start with AD first. So AD is the D is the orthocenter of triangle AFX. So as such, it is 2 times R. Hey, AFX has the same circumradius as ABC, right? So 2R times cosine of angle FAX, and similarly, well, at the expense of ruining the picture, yeah, okay, let's ruin it, I guess. Okay, so AE is equal to 2R times cosine of angle, well, this one is, where was I? Yeah, this is for triangle GAY, so that's just angle GAY. And boom, because we know that AD is equal to AE, the left-hand sides are equal, the right-hand sides should be equal. So therefore, we get that angle FAX is equal to GAY. So let's mark those two angles. So FAX is this angle over here, and where the heck? Oh yeah, here, this one. GAY is this angle. Nice. So those two angles are congruent. That suggests that arc Fy is equal to minor arc GX, right? Because the midsection is the same in both of them, so therefore the sides are also congruent. So those two sides are congruent, so therefore Fy is equal to Gx. If Fy is equal to Gx, okay, so therefore so let's write that down. Arc Fy is equal to arc Gx, but then we can just translate this into angles. So Fy is subtended by this angle Fgy, and arc Gx is subtended by this angle Xfg, right? So let's write that down as well. So far we have found that angle XGF, YGF, that's a Y. Okay, YGF is equal to or congruent to XFG, angle XFG. But now we are in business because look at, let's start with this one. This angle, because we have a right triangle here. Oh gosh. Yeah, so let's focus on this right triangle. So what do I want to call this point? Q, P, what? P? Okay, there you go. I call this one P, and let's better call this one as Q. I know that's tiny. Okay, so that doesn't even show up. Okay, let's go back. Come on. All right, so that tiny angle here. Oops, there you go. That's a Q. Awesome. So let's start with that P thing. If this angle here is YGF, which it is, so therefore this guy here is 90 minus YGF, right? And this one is also 90 minus YGF. Does that make sense? So so basically what we can do is, hey, if that's the case, I can just subtract those angles from 90. So I have 90 minus YGF is equal to, does that make sense? And I can do the same thing on this one. XFG is just 90 minus let's just do it the other way around. So sorry for that. So YGF can be represented as 90 minus GPK. Okay, let's just write it like that. Otherwise it will be confusing. So this is that one. And similarly, XFG, we can write it as 90 minus angle FQL. And obviously I can, the 90 is cancelled, so that would imply FQL, that's a Q, is equal to angle GPX. But wait, angle G, what, that's not even an X, that's a K. Oh my god, GPK, sorry for that. Okay, so that's a K, not an X. Okay, there you go. Okay, but then by vertical angles, okay, so that's also suggests that FQL is the same thing as ALP. Yes, that's exactly what I needed. ALP, okay, let me check it again. Okay, that's definitely wrong. AQP, so that point is a Q, sorry. Vertical angle, so this angle and this angle are vertical angles. AQP, sorry for that. AQP, and similarly vertical angles, I already marked this one, so that angle, this angle, okay, and GPK, sorry for that, APL. angle APL. Ha ha ha. Those two angles are congruent, but if you focus your attention on triangle ALP, those angles are just 90 minus A over 2. If they are equal, right? So they must be both 90 minus A over 2. The same thing here, 90 minus A over 2. Hey, those are also 90 minus A over 2, right? Because, okay, or you can just say it by similarity, right? So because those two angles are congruent, AL is equal to AP, they are isosceles. AD is equal to AE, this is isosceles as well, suggests that DE is parallel to LP, right? LP is the same thing as FG. Alternatively, you can just calculate these angles. Like I said, these are just 90 minus A over 2, and boom, again we have corresponding angles, suggesting that DE is parallel to FG, and we are done with this second solution as well.